All right, welcome to 3D GV seminar series. Today we have Saurabh Gupta from UIUC. Saurabh is a system professor in the ECE department. He has done many great work. In fact, I remember he started with a lot of great work in 3D scene understanding. Recently, he moved the research direction a little bit, focusing on the visual navigation, 3D, and representations with visual navigation. In fact, he's where he also involved the foundational work in this direction. And he has won many awards, including the Google PhD Fellowship in Computer Vision and very recently Amazon Research Award. Okay. So let's welcome.
Yeah, thanks a lot, Kishin, for that kind introduction. I'm extremely excited to be here today to share some of my work. But before I start, I want to thank the organizers for putting together an amazing series of talks and panel discussions. And this has really helped keep the community together, even in the current challenging times. I've enjoyed many of the talks and the panel discussions, and I'm hoping today will be as much fun. And I'm especially looking forward to questions from all the panelists and all the audience towards the end of the talk. Okay, so today I want to talk about representations for visual navigation and how to train them. And before I start, we have clearly made large progress in computer vision over the last, not just many years, but many decades, right? Given one or many images, we have gotten pretty good at predicting the 3D shape and pose for people, objects, and places, right? And in doing so, we have had to tackle and understand a number of scientific questions. For example, how do you represent rotations? Or where does supervision come from? And so forth. But among these, I think the central question that we all have debated many times over and over again is this question of what is the right 3D representation? Should it be voxels? Should it be meshes? Should it be layered depth images? Or should it be implicit functions? Right. And as Kishin said, in some of my past work, I've worked on 3D representations and so forth myself. And I think I was always bothered by this question, what are we doing 3D for? And in some sense, what is the right representation ends up being, we don't want it, but it ends up being a function of what are we going to use this representation for, right? So for example, if you consider applications such as, applications in computer graphics or view synthesis or making measurements in the world, right? If we consider most of these applications over there, what we require is very high fidelity reconstructions, if you will, which look good, which can actually be used for, let's say, placing an object inside a game engine or animating characters and so forth, right? So there is like a lot of work in 3D has, when we talk about these representations, quite a bit of this work is geared towards applications of this form, which by all means are very necessary and essential, right? And right, that's that. But I think I was always faced with this question, which is that humans and animals don't really build representations of the world around them for purposes of re-rendering them and so forth, right? They do it for the purpose of acting in the world. And so in today's talk, what I want to do is basically focus on what, in my view, are some promising directions for building representations for places that can afford navigation in novel environments, right? So that's kind of what I'll try to focus on today. Yeah, so before I start, maybe let me tell you what are basic navigation problems that I will try to tackle, or like our approaches are geared towards. And yeah, so for that, let's consider there's a robot and it has a first-person camera. And we have brought this robot into a new environment that this robot has never been in before. And what we want this robot to do is to do useful things, let's say, right? So we might give it a point goal, which is go 300 feet north, 400 feet east. And we want this robot to autonomously be able to do that. Or we could specify the goal in slightly different ways, which is we can give it an image of a target location, and we want this robot to automatically go and find this object for us, go to the location from which this image was taken. Or it could be an object goal, which is we can ask this robot to go and find a chair, right? That could be another goal. Or it could be loser, which is just go and explore the environment, build a map for it, or something like that. So I'll basically be focusing on tasks which look something like this, which is robot has been dropped into a novel environment, and basically it has been given one of these tasks that we want to do. Right? Now, of course, the question of what are the right representations for these tasks is not a new one. In fact, it has been looked at in robotics literature for the last 40 years. And the dominant solution that has emerged is what we call SLAM, right? And this is what a SLAM system will look like. A classical solution will break this problem into two subproblems. One, that of building a map where we take observed images and build a 3D reconstruction of the world, much like lots of representations that we aspire to build in 3D computer vision ourselves, right? So there's this process of mapping. And once we have done the mapping, then we have path planning, where we essentially take the 3D reconstruction and try to plan paths that will convey a robot from its current location to a desired target location, right? And I should note, breaking this problem into these two subproblems of mapping and planning has allowed the community to make large progress, both in mapping, sophisticated algorithms for mapping from lots of different sensors, and path planning and the like, right? However, this choice of 3D geometric representations as a way of representing the world has some drawbacks, and I'll talk a little bit about that, and those will essentially motivate the representations that we will be building in this talk. Right? So first of all, I think it's possible that full 3D reconstruction of the world might actually be unnecessary if all that we want to do is to navigate around the world, right? So for example, consider the scene, do I really need to tediously reconstruct everything that is on top of this table if all that I wanted to do was to walk past it? Perhaps not, right? So this kind of one example. Over here, I'm trying to argue that a full 3D reconstruction of the world might not be necessary. But this goes further, actually, which is that full camera estimation might also be unnecessary in the following sense, right? So this is some experiments that were done by Stanley Milgram in 1976, where what he did was asked people living in Paris to draw their understanding of what is where in Paris. And I've never been to Paris, but from his paper and his book, he basically describes that there is a river called Seine River. And it turned out that systematically people would underestimate the river's curvature, right? So this broken line is the actual river, and the dotted line is what people drew. So they underestimated the curvature of this river systematically, right? Now, I mean, this is seeming to suggest that people can operate in the world perfectly fine without necessarily having an accurate metric 3D sense of what is where in the world, right? And this, again, in context of 3D computer vision, I mean, I would regard this as that pose estimation and, geometrically consistent global pose estimation and so forth might actually also maybe is unnecessary for the task of, if all I wanted to do was to move around, right? I mean, given we are all living in this COVID times, I mean, I have spent 24/7 52 weeks at my place, and yet I can perfectly go from one part of my apartment to another, but I still don't know how far is everything from one thing to another, right? This again, I don't know. I mean, I can operate perfectly fine in the world, but I don't know metric 3D information and so forth, right? So in that sense, our choice of full metrically accurate, spatially consistent 3D metric worlds may not be necessary for, maybe an overkill in some sense if we want to do robot navigation, right? At the same time, it also lacks something, right? If we just go with a 3D reconstruction of the world, and I mean, that also lacks something. What it lacks is semantics, right? So for example, if you have a robot and let's say it's only reasoning about things that are directly visible, then it has no way of inferring that there is a hallway behind these cubicle walls and that this hallway goes in both directions, left and right, right? Whereas as humans, we can actually very well make the speculation that there is going to be free space in the form of a hallway behind these cubicle walls. And I just know that not because I have been in this particular office, but because I have been in lots and lots of other offices in my past life that allow me to make meaningful speculations about what is there in this particular environment, even though I've not observed it. Right? Similarly, there's this other aspect, which is, let's say I'm trying to find a bathroom in a new restaurant that just reopened after COVID or whatever. And again, even if I give you a full 3D reconstruction of what you're seeing, right? The answer to this question, where should I go if I have to find a bathroom, right, is not easily answered, right? I mean, as humans, I can certainly say that, I've not been into either of these restaurants before, but if I were to make a guess, I would say that going straight ahead in the image on the left and then turning left might lead you to a bathroom, whereas going straight ahead in this image on the right might not very likely lead you to a bathroom, right? And this is, again, some amount of semantics that is coming at play, which is, given what we are seeing, we can make speculations about where objects could be, and those could be useful cues for a robot to navigate in the world and so forth, right? Okay, so this is kind of what motivates our representations for places for navigating in novel environments, where we will like to augment metric representations with semantic reasoning. So I'll show some work where we can actually augment metric representations with some semantic features and so forth, which can capture some sort of predictions for beyond what you're seeing right now, or semantic predictions. Then I'll talk about how we can relax the need for metric representations for doing navigation, right? So that's kind of going to be my second part. And towards the end, I'll try to say how we can scale up training of representations, right? I mean, whenever we talk about semantics, there's always this question of how do you get those labels for those semantics? How do you get training data for those semantics? And yeah, so in the third part, I'll basically try to say how we can get around this need for extensive semantic annotations and so forth for building these representations. And while I'm doing this, I think what I'll try to do is I'll try to operationalize insights from classical robotics and sprinkle in, learning wherever is necessary in order to get things to work the way we want them to work, right? So throughout this talk, you will see this common theme that we are not in any way replacing architectures or frameworks that have been proposed in classical robotics, but we are augmenting them with machine learning in just the right way, in just the right amount that you can actually get systems which benefit from both classical robotics and machine learned priors. Right? Okay, yeah, so I think these are the three things that I'd like to talk about today. Yeah, so let me tell you about how can we augment metric representations with semantic information. And this is some work that we did some time ago now. The basic setup is we have we want this robot to navigate. There is the current observation that the robot is seeing. There is the goal that the robot wants to eventually achieve. And what we are going to do is we are going to be building neural network policies which take in this information and output actions that the robot should take. Now, these neural network policies will over time be building a spatial representation of the world. And in fact, they will use a mapping module to build this representation. And then on top of this representation, we'll use a planner which takes in the representation along with the goal specification to output actions that the robot should take. Right? And once the robot outputs this action, it's going to experience a new image along with some ego motion that occurred between the previous time step and the current time step. And then we'll repeat this process over again. But in this time, the mapper will not just take in the previous viewer's input, but also the ego motion and the spatial representation from the previous time step, output an updated spatial representation. Again, we'll use that with a planner to output actions and so forth. And this process will continue on over and over again. Right? So this is the basic paradigm. And again, this is very similar to mapping and planning that I described in classical literature, except for this key distinction that we can make these mapping and planning modules to be differentiable functions. And what that allows us to do is that we can train the representation for the end task of navigation, right? And that can allow us to go from handcrafted obstacle maps to task-driven semantic maps, which can capture these semantic properties, more abstract semantic properties, which I was referring to in the earlier slides. Right? So that's kind of the advantage of building representations of this particular form. Okay, good. I'll just go into a little more detail on this so that we have the right context when we're talking about future things. Yeah. So the spatial representation that we are building here is actually very much like a semantic voxel map, if you will, where there is a feature descriptor that describes a part of space relative to the agent, right? So we are going to be, each grid in this feature map is representing some space, and we are storing a feature vector at that particular location. We're also storing a confidence value, which is how confident are we about those features. And again, if we are building a representation, we need to know where the agent is. The agent is going to be in the center looking upwards all the time, right? Okay, now this is my representation. Now the question is, how do I build this representation, right? And for that, there's this mapping module, which takes in the representation from the previous time step and adds in information from the current time step, right? So we have the image along with the ego motion. We use the ego motion to warp the representation such that the agent is again at the center and looking upwards, right? So if the agent rotated right, then we rotate the representation left, and then again, the agent is at the center and we are going. Now we basically take the image and incorporate whatever information we can get from this image into our representation. So we have an encoder-decoder network. It takes us from the first person view of the image, first person view image to like a top-down view where we are pasting in whatever additional information this view gives us, and then we basically average these two representations that we get to get the updated representation. Okay, so this is kind of the mapping module, and analogously there's a planning module, and again let me tell you a little bit more about that. I mean, this planner is actually based on Bellman updates and Bellman equations, which essentially, I mean, you're in a map, you're trying to get somewhere. Planning can actually be, I mean, if you know that if you want to get to this location, what you're trying to do is you're trying to estimate a value of how easy is it to get to the goal location from any given location. So if you're at the goal location, you know that you can get there already. But if you're one step away from the goal location, then also you can get there pretty quickly. And you can do this reasoning recursively, and this is the process of value iteration. And it turns out this can actually be written down in a neural network language, where you look at spatial context around the location, and you look at the connectivity information, free space information around this location, and you look at the values that you have, the neighboring pixels have, and you use all of those to make a prediction for what is the value for the current for the location, right? And it turns out all of this is local computation that you can think of as doing via convolutions and channel-wise max pooling, and I mean that makes it very easy to think of planners as differentiable components that you can plug into a network. Okay? Once you have a value map, you can basically take a local neighborhood around the agent's location, and the local neighborhood, you can look at the gradients of this value or whatever, and that can tell you in what is the right action you should take at this location in order to go to the target. Okay? Yeah, okay. So basically, this is kind of the full policy architecture, right? Now, I mean, in some sense, what we have is this is the architecture. I told you about the mapper and I told you about the plan. And because everything is differentiable, now we can start learning the representations that we have. Now, the question is, where do we get training data for learning these representations? And for that, we basically built a simulator based on scans from real world environments. And in these scans, you can simulate a robot. And these scans, right, you can simulate the robot's view and robot's motion. You can compute ground truth statistics or ground truth free space maps, ground truth of where objects are, and so forth. And basically, you can cook up a reasonably realistic simulation environment in which you can train these policies, right? So we made some of these simulation environments some number of years ago. I mean, and these are based on Matterport scans and so forth. And I mean, if I were to redo this work right now, I would use something like AI Habitat and all the other Gibson or AI2 Thor, any kind of these simulation environments that are out there right now. But the basic setup is the same, that we are going to be training these policies on some training environment. And the way this training works is that I have a map. I can sample training problems. For example, I can say that my robot starts from this location and it wants to go to the star location. Let's say the star location was the delta x, delta y that it was given, or it was the location of a particular object in this particular environment. And now, because I know the ground truths in these maps, I can compute the ground truth trajectory, and I can use that to compute the optimal action. And I can train the policy that I described I can train this policy to predict the same action that an optimal planner, which has all the information about the environment, would take, right? And I mean, this you can train with standard backpropagation, and you get your policy. Right? Yeah, so when we trained these policies back in the day, we were very excited. We could actually, when you had depth input, we could match how good classical methods were doing. But when we didn't have depth input, then we could do much better, because during the course of training of these policies, the neural networks will learn about free space and so forth, and how to interpret them from RGB images and the like. Right? So this was pretty exciting at that time. Another thing which was interesting here is that we could swap out the goal specification to make it a more semantic goal task, right? So we could now instead train this policy not for going to a delta x, delta y location, but instead to an object of interest, right? So we could say that, okay, I want to train a policy which goes and finds chairs in an environment, right? So I can swap out this goal specification, and I can plug in that I can retrain my policy. And this did reasonably well. So this is some runs in this kind of the simulation environment that I was describing to you, where we are trying to look for chairs. And the general policy it learns is I should go inside a conference room or inside some kind of a room, because rooms typically have chairs, right? So here's another example, which it is in a hallway and it's trying to look for chairs. And it doesn't quite see that there is a chair inside this particular room. It decides to walk in because chairs typically have occur inside rooms, right? And so it can kind of learn this kind of semantics of where objects are in images only through the course of training, right? Yeah, and I mean, we can measure performance. Over here, we had a much larger improvement over classical methods, which would only be able to find the chair once you are actually seeing the chair. So this was actually pretty exciting. Right? I mean, it turns out that during the course of training of these models, the model would actually learn about some of these semantics that I was alluding to earlier, right? So I was earlier saying that, if I am inside, I want to be able to make predictions for things which I may not have explicitly seen in this environment, but I can make predictions for what is behind whether there is free space behind a wall or not, right? So in some sense, that's kind of what I'm trying to show over here, which is that this is the first image that the agent sees, and it can actually make a reasonable prediction for free space behind this particular wall. Now, we never trained this agent for predicting free space or anything like that. All we get at the end of the day is abstract representations inside the network. But you can train a decoder which can decode those abstract representations into quantities that might be of interest, or into quantities that you might be curious whether your network has learned or not, right? So in this case, we trained it for predicting free space, and it turns out that the representations that the policy was learning could actually encode that there is likely free space behind a particular behind this particular wall, right? So in this case, again, the agent is in the center looking upwards, and this is prediction for free space. If this agent were to walk further and exit the room, it turns out that you can keep going further, and you will notice that this is actually a consistent kind of observation, that this is a room. It has not seen inside the room yet, but it can make prediction that there is likely going to be free space over here, because a doorway tells you that there is a room and that you can go in and so forth. Okay? You can do more than free space, turns out. You can actually distinguish between whether this is free space inside a hallway or is this free space inside a room, right? So this agent starts inside a hallway, but then it enters into a room. And as you see, that this is prediction for whether this is free space inside a hallway, this prediction for whether this is free space inside a room, and it kind of it is able to make prediction that there is some free space, that it's inside a room right now. So in some sense, yeah, right. So right. So I think I mean, when we did this work, I think we were very excited that, oh, we can actually do spatial reasoning. I mean, we borrowed the mapping and planning architecture from classical SLAM solutions, but then we could inject semantic reasoning into it. And the semantic reasoning was happening, was emerging inside the network purely for the reason of acting in the world, right? We didn't say what it should represent. It was able to automatically learn what it should represent by the process of what is useful for the end task. Okay? So these were things which we were pretty excited about. But it turns out that, right, so what we have relaxed so far is we don't require it to explicitly estimate geometry. We don't require it to, we don't limit our networks to only represent geometry. But we are still assuming that we will have accurate pose information at test time, right? Or at training time, in fact. Right? And this is not unreasonable. You could be running a SLAM system under the hood, which will continuously localize the robot and make sure that there's not too much pose error, and such that your maps that you generate are, spatially consistent with the observations and so forth. But it is, again, as I said, I mean, maybe this is an overkill, right? So this is kind of one of the limitations that that this particular work suffers from. But there are other limitations as well, right? For example, the training of these policies was completely interactive. We were not quite using reinforcement learning, but we were using Dagger, which is a form of imitation learning, robust to distribution shift and so forth. But what that required is that you have to have a simulator in order to be training these policies, right? And again, I mean, it pushed the burden from test time to training time, right? At test time, you don't need to do too much, but at training time, you need to work really, really hard in order to, solve the problem or learn how to solve the problem, right? And I guess like a related problem is if you wanted to do very long horizon tasks, right? So let's say your goal was hundreds of steps away. Now over there, to be training a policy which reasons at the horizon of hundreds of time steps becomes hard, right? In our case, because we were using imitation learning, that didn't bother us too much, but it still slowed down training and so forth. And, it still becomes problematic, right? Right. So I think what I want to talk about next is how can we relax, or how can relax some of these assumptions that we were making, and can we go towards representations which do not necessarily need spatially consistent global maps, which is what this kind of work was necessitating, right? Right. So I think that's kind of what I'm going to talk about in the next 15-20 minutes, which is how can we build representations which don't need a spatially consistent global map in order to operate. And I will do this in context of image goals. I mean, in fact, I'll later on show that you can actually do this for object goals and so forth as well. I mean, I just have a variety of different problems just to convince you that these techniques can actually solve not just one or two navigation problems, but a variety of navigation problems. Right? Okay, so this is kind of the problem, which is we will try to find images, right? So the agent will be given an image, and its task would be to go to a location in this environment where this image is coming from, right? And this is some work that appeared at CVPR last year, at CVPR 2020, right? Okay. So this is kind of the problem statement. As I said, we have a source image, which is where we are right now. And we have been given a target image, and we want to output actions which will convey the robot from the current location to the target location, right? And in particular, because we want to understand this notion of do we need spatially consistent representations, we are going to be introducing actuation noise, which is that the robot doesn't precisely know how much it has moved between the different steps, right? It doesn't know, right? As it takes a step, it doesn't exactly know how much it has moved. And again, this is actually true for robots themselves. Like if you run a robot for very long amount of time, I mean, eventually you will have drift. I mean, you can use local correction, you can use, right? Local correction will always suffer from this, that over time you will accumulate error. You can do global things to actually get rid of this error, but that's expensive and can fail and all of that, right? So it's not that we are not cooking up a synthetic problem. I mean, this occurs with real robots if you try to do navigation on physical platforms, right? Okay, good. So what's kind of this representation? So this representation is actually going to be a topological representation where we are going to be building a graph of space, right? So as we are going along, we are going to be storing different locations. We are going to be storing images at different locations. And for simplicity, we are in this work working with panoramas. So we are going to be storing panoramas at different locations. The other aspect of this topological graph is that so at each node, I have the panorama, but then different nodes are connected to one another through some sense of what is the relative pose between two images, right? Right. Okay. So that's kind of the graph part. Now, and again, this graph is reminiscent of topological graphs in robotics. What we are augmenting this graph with is some number of learned functions which will allow us to do semantic reasoning on top of these graphs, right? So the first semantic function that we include here is this function which can make predictions about geometry, right? So given a panorama, it can predict what are different directions in which I can explore in this environment if I wanted to, right? So this is kind of measuring how far can you go in different directions from this current location, right? So that's kind of this function fg. And wherever there is high prediction for this function, wherever it feels that there is quite a bit of distance I can go in this direction, I'll be placing something that I will call a ghost node at that particular location, right? Okay, good. Another function that we have is this semantic prediction function, which basically tries to make a prediction for how close is a particular direction to the target that I want. So as I said, in this work, we are working with image goal tasks where we have the image of a goal location that we are trying to get to. And the semantic prediction function is essentially takes in the panorama at this current node and the goal image, and it tries to make a prediction. If I were to go in a particular direction from the current image, how likely is it that I will be at the goal location, right? So that's a semantic prediction function, which again outputs like a value in each of the different directions. So for each ghost node where the agent could actually go to, I will actually have a value, which is the semantic prediction score, which is, how likely is it for me to get to the goal image if I were to go in this particular direction. Okay, good. Yeah, so that's kind of what we've augmented. I guess there's another function, which is a localization function, which takes the current observation and the observations that have been stored at the different nodes and tries to say whether you are at the same node or you are very far away from all existing nodes, right? So that's this function, localization function fn, right? Okay, so that's kind of this representation. And this representation entirely relies on these four functions. Fg, which is this geometric prediction, Fs, which is the semantic prediction, which predicts closeness to targets, Fr, which is relative pose, given two images, how far are they, and Fl, which is the localization function, which tells you, right, like whether you are at the same location or not, right? Okay, so you have these four functions. Now, let me tell you a little bit about how we can use this representation, right? So the way we use this representation is through a hierarchical policy, where we have a high-level policy and a low-level policy. This high-level policy decides where to go next and emits a short-term goal. And the low-level policy takes this short-term goal and tries to output actions in order to achieve this short-term goal. This high-level policy, when it's trying to do what it is doing, it is going to be building this representation that I described to you. And this representation keeps track of visited nodes, it keeps track of ghost nodes and the values predicted by f of s, right, for different directions, right? So basically, let's say these were the two nodes. So this representation, this high-level policy is building this representation. It has these different nodes. It knows where the agent is right now. It makes predictions for where can the agent go from these nodes. and how likely is it for me to find the goal image from these different directions in which I could go, right? And based on these predictions for these values, this high-level policy decides that, oh, I will be sampling, this is the most promising direction that I should go to. It samples this location, it computes a pose, which is, where should I go in order to get to this particular location? It passes on this delta pose to the low-level policy, which predicts the local occupancy and plans paths, right? And I mean, that's kind of one way of thinking about this, that you can build a local occupancy map using, by predicting local occupancy information or using depth sensors, whatever you have. And you can construct a plan based on that will output actions that the policy should take. And once it has reached the local goal, it can pass the control back to the high-level policy, right? There's also the option of learning a low-level controller, which if time permits, I'll get to. But for now, you can just assume that we are building a local occupancy map in order to do this kind of path planning, right? Okay. Yeah, so that's kind of what this policy looks like. I mean, there's some details on how do you build this representation. I mean, building this representation involves updating the graph, and that basically is determined by that if the current location is already at a particular node in this graph, then you don't do anything. If it is not one of the nodes in the graph already, you add this node, right? So it's as simple as that. And again, this function FL, the localization function, is used to do this, to determine whether the current image is close enough to the current image or not, and so forth, right? Okay, right. So that's this building the representation part. Again, as I said, this FG function, which predicts where you can go from each of the nodes, represents this free space around you. And I mean, that's used for getting these ghost nodes and so forth. Right? Okay, so once we have this, what does it take for me to build this representation? It turns out I just need to be able to train these 4 functions, and then I'm done. And these 4 functions in this work, we are going to be training with supervised training, right? So again, we have a simulation environment in which we can make queries of the form, where is free space, right? If you have a full-blown simulation environment, given an image at a current location, you can compute in what directions can I go from over here, right? You can actually compute, given a pair of images, which direction is, how promising is each direction for getting to different goals in the environment, right? You can compute supervision for, what is the relative pose between 2 images, and you can compute supervision for whether you are localizing or not, right? So it turns out you can actually train this whole representation without any reinforcement learning, no interaction. I mean, not just without reinforcement learning, but also without any interaction. You don't need to interact with the environment. You can just offline collect training data, and you can train the model. And once you've trained these 4 functions, you're done, right? So that's kind of one advantage of this, right? So let's see what this function actually learns. So on the top, you are seeing the source image, which is where you are right now. In the bottom, you are seeing the target image, which is where you want to go to. And this is the prediction for the semantic score predictor function, right? So you can notice that it has non-zero predictions in locations in which you can further explore, right? So these doorways that you are seeing. And you can see that there is a high prediction for this middle doorway. And that's not so surprising, because the target image you can kind of see in a very blurred version in this through this doorway, right? So that's not that bad, right? So it kind of does something sensible. But more interestingly, if you give it an image which is even not directly visible from over here, it can still make a reasonable prediction, right? So you will notice the predictions are not as peaky anymore, but again, the image on the bottom, it doesn't quite see a bed through the source image on the top that you're seeing, but it makes a prediction that it's possible that this bedroom kind of region might be if I follow this hallway that I'm seeing on the left-hand side, right? That is like a more promising way, in a place where I could find like a bedroom than these other 2, right? And this is again the semantic prediction that I was talking about earlier, right? So here is, you can see this policy in action. you have this goal image. You have the current observation, and this is the goal image. You're starting from this location, and you want to get to this location. Again, this map is only for our visualization. The agent is only seeing images as it is going along, and it has only access to approximate noisy odometry, if you will, right? Yeah, so this is basically, this is the image. These are basically the locations, the geometric predictions that it made. It then sampled, this particular location that I will go in this particular direction. It takes some number of steps towards that direction, and then it samples another view. And that view, basically, using that view, it samples another goal in order to go to. It tries to go there, and it repeats this process over and over again. And over time, it's actually able to get to the desired target location, right? Okay. Yeah, so I can maybe also show you some numbers. So here we are measuring performance in terms of how efficiently can you find images in novel environments. And we are making comparisons to vanilla neural network memory-based models. We are making comparisons to metric maps and topological map, which is what I presented just now. And it turns out that map-based methods work much better than vanilla neural network memory-based methods. And this we have found not just in this work, but also in the previous work that I described. So it's not that surprising. But this topological version actually works better at, when we are building pure occupancy maps, which don't have any semantics, but topological maps, the way that we are building over here, they have some semantics, so they can actually get better performance than not using semantics. So that's also to expect, but good to confirm. But I think the most interesting numbers to me in this table is this comparison, which shows robustness to noise, right? So we are comparing two settings where you have RGBD images with noise and RGBD images as input without noise, right? And you notice that map-based methods work much better. There is a large drop in performance when you go from no noise version to noisy versions, right? For map-based methods. But for our method, because we are baking in this robustness to noise, we are not relying on precisely knowing where you are through the course of your trajectory. The drop in performance for our method is much less, which to me is like a very promising sign in the sense that perhaps knowing exactly where you are might not be as necessary if all you care about is moving around in the world, right? At least in the experiments that we have done in this context. You can actually do further analysis, and this is to show that the utility of the score function and the utility of the graph. So blue line shows the full system that we have. In this plot, we are doing number of sequential goals. We are not just asking the agent to go to one goal, we are asking the agent to go to multiple goals in the same environment. So what we see is that when you try to do the first goal, it turns out that having this score function is actually very useful, right? If you have not had any experience with the environment, knowing what are useful directions to explore helps you quite a bit, right? So you see quite a bit of gap in performance between our method and the baselines when you have because of the score that we have. But towards the end of when you're doing many goals in the environment, at that point you have experienced this environment in quite some right? You have had quite a lot of experience with this environment, and at this point, knowing like this expectation, like the score function for where should you go, matters less than not having it, right? Because you very likely have seen images that already occur in the environment, and so this semantic prediction might not be as useful. However, at the same time, just having the score function is not enough, right? You need to have this topological representation, right? If you don't have this topological representation, which is this red line, you ignore images that you have seen in the past, you see a very large drop in performance if you were to have done that. And that's, again, to expect, but good to confirm. Right? Okay, so I guess this was this second attempt at building representation for places where we got rid of some of the limitations that we had earlier, right? We were able to get to a scheme which was robust to pose estimation error. We, in fact, did not rely on interactive training. We could do things with offline supervised training, right? You don't need interaction. You can just offline gather data and you're done. And also this modularization of having a hierarchical policy and a low-level policy allowed for, I guess if you're doing supervised training, there's no horizons, but this kind of modularization can help with training to some degree, right? There was still one caveat, which is it still requires a simulator, right? The queries that we were making, that in what directions can I go and what directions are promising for finding objects or going to an image, that was still being trained inside a simulator, right? And so, I mean, I guess very briefly, what I'd like to tell you about is how can we simplify and scale up training further, right? Such that we don't need a simulator. And again, this is going to rely on this, on these 4 functions. What we are going to do is we are going to figure out alternative ways of training the semantic prediction function. And like the earlier functions, which are to do with geometry, there's a lot of work which tries to study how you can train relative pose estimators, localizers, and so forth without supervision in a self-supervised fashion. So we're going to rely on some, I mean, those problems, I believe, have been tackled to some degree in the community already. What we are going to focus is on how can you learn this semantic prediction function, not through simulation, but through other means, right? And the way we are going to do this is by actually doing this by watching videos on YouTube, right? And this is some work that appeared at NeurIPS earlier last year. And yeah, so basically we are going to try to learn this semantic score function by watching YouTube videos, right? And I mean, before going into too much detail, I'll like to give you a basic intuition that at the end of the day, these semantic functions that we are trying to learn are essentially capturing co-occurrences, spatial co-occurrences, right? So if we can mine these spatial co-occurrences in some other way, then we are done, right? Then we don't need simulation or anything like that. And that's kind of what we did over here. So if you have a video, right? Let's say there's a video that you walk in and you are seeing someone's living room and you're walking around and so forth. So let's say you are given this video and you are trying to learn cues for finding a couch, right? Now it turns out, right? So that's kind of the setup, and you're trying to find couches. Now it turns out that if you are seeing a couch already, that means this is a pretty good cue for there being a couch, right? I mean, if you already see a couch, then you know how to get to a couch, right? Then you can just walk towards it and you're done, right? But now let's look at this middle image, right? If you're seeing a part of a couch, that is still pretty good. If you are seeing a part of an object, you can still try to go there and you can, kind of get to a couch. But I think the interesting bit is, even if you're seeing only this television, that also tells you quite a bit of where a couch could be, right? And because of this co-occurrence, right? If I were to simply go in the direction of this television, I know that televisions co-occur with couches. And if I find a television, then it's possible that there is a couch around it. And maybe I should go in that direction if I'm trying to find a couch, right? So I think the semantic cues that we have been talking about, which can make predictions for where objects are essentially these spatial co-occurrences cues. And it's very reasonable to think that we can actually mine them from videos. And that's kind of what we are going to be doing. We are going to develop a machinery for doing this, for mining these things from videos. I guess in interest of time, I won't go into all the nitty-gritty details. I mean, but videos don't quite come with action labels. It's not clear how do you use these videos for learning how to act in the world. We don't know what are the goals and intents of whoever was collecting this particular video. And the depicted trajectories might actually not be optimal. It turns out all of these problems can go away if you use 2 tricks. One trick is you synthesize labels. You label image pairs with the action that was happening by labeling things with the inverse model. That's kind of one trick. The second trick is you can use Q learning on the dataset that you have, and that will learn for you the optimal behavior, even though the depicted behavior may be suboptimal. And there's a beautiful result from 89. And if you don't, I would encourage you to read that paper, right? And that's kind of what we basically did. We took real estate tours from YouTube. Turns out there is a reason why people upload them to YouTube, and you can get some of them from YouTube. Here is the video. You do some action grounding, which is you run an inverse model, which you can train by relatively small amounts of effort. Or you could actually use classical structure from motion, and you can get actions, did you move forward, did you turn left, or did you turn right, in order to go from one frame to the other, right? So that's not so hard to train. You can also use classical methods, right? So I get basically image action pairs. I basically label goals. I run an object detector that has been trained on COCO dataset, and I get does this image contain an object of interest or not. And I basically put all of these things together: image, action, next image, and whether did I get a reward or not. And this basically gives me a Q learning quadruple. And now I can basically do this magic, which is Q learning with this. And this will learn a function, which is going to be, it will learn to me the optimal function, which measures how close I am to the target object, right? And that kind of learns the function, right? So let me show you an example. So on the bottom, I'm showing the prediction for the values that this particular method learns. And I'm doing it for object goal in this case. So I have different categories. And this is the panorama that is being input. What we can see is that if you're trying to look for a chair, couch, or a dining table, it has high prediction in this left corner. And that's pretty good because you can already see a couch, and chairs can co-occur with couches. So chair predictions is high. You can kind of see a dining table. So those predictions are also high. So that's pretty good. But what's again interesting is that when you try to see where should I head for finding a bed or a bathroom, it's not seeing any either in either of these images, but it makes a high prediction for going down this hallway. And that is for this reason that it's possible that you're kind of in a living room like area, and to find a bedroom, you might go down a hallway and there may be a bedroom attached to one of the hallways, right? And this is exactly the semantic cues we wanted to gather, and it turns out we can actually get that, right? Here's some more visualizations. Yeah, and again, we just take this function and we drop it into the hierarchical policy that I described to you earlier, and we get pretty good performance, right? So here is basically some measure of how well you're doing, and here is number of frames of direct interaction for training. And with these two lines, I'm plotting what reinforcement learning and these learning from experience kind of techniques do. And very close to zero is basically where our methods are, because they don't require any very much direct interaction for training. And they actually do pretty well, in fact, much better than these methods, which are actually using reinforcement learning, just because we are able to leverage large scale data sets from YouTube, right? Okay, some relations which I'll skip in ahead, interest of time. Here is a video where we have learned a policy for finding couches, right? So it goes around, it's building this kind of a topological map, which I described earlier, and it's making use of these semantic predictions that we have learned through training on videos from YouTube. And so it can actually do a reasonable job at finding objects of interest, right? Yeah, so goes out in the hallway, tries to find it over there, it's able to find it. Okay, good. Yeah, so I think in some sense, what I've shown you is how do we build representation for places. You can do, right? These representations should be able to do spatial reasoning, semantic reasoning. They should be robust to pose error. They are, modularizing them helps us training some part somewhere, some other part somewhere, allows better use of data that's already available. And I showed you how we can build these representations from in the white videos. I think very, very briefly, I think I mentioned this low-level policy. And what we used in some of this work is local, you build a local map and then you go from there. It turns out you can actually learn these functions as well. And I guess I won't quite go into all the details over here, but there is merit in learning these functions because they can, if you're learning this function from RGB images, they can actually work in scenarios where your estimates from depth sensors are not very good, right? So in challenging environments, when you have direct sunlight or you have lots of clutter, your depth sensors might not work very well, but this policy that you've learned can actually still successfully work in such. And and it turns out you can actually also use them in outdoor settings for navigation in fields. UIUC is in the middle of lots of cornfields. So we have lots of problems in that domain over here. And we, in fact, recently showed that you can actually use learning in context of low-level controllers to learn policies on top of RGB sensors, which can outperform policies based on LiDAR sensors, in the sense that you have to intervene with robots much less, and at the same time having much less sensing cost, right? And again, I guess I'll show just these teaser videos, and I encourage you to read the paper when it comes out. Yeah, I think that concludes my talk. I think what I showed basically is like how can we think of building representations for places that can afford navigation in novel environments. I showed how we can augment metric representations with semantic reasoning, how we can relax the need for explicit metric representations, and how we can scale up training of such representations by using videos. I guess I briefly showed role of learning in low-level controllers as well, but that's it. Right? And with that, I'd like to thank all my collaborators and funding sources. And I'm happy to take any questions from the panelists or from YouTube and so forth. Thank you.
Okay, thanks, Sarah, for this great talk. I learned quite a bit. So today we are great honored to have two panelists, Katerina from CMU and Hao Su from UCSD joining us. So as usual, so we will start with two questions from YouTube. Okay, then we'll open the questions to panelists. So the first question is from Chuhan Zhou. Great work. I'm curious how these noise are produced. Right? I guess there's some procedure for generating noise. These noise added during the test time or during training. So this is really about one of your work.
Yeah, that's a very good question. So this noise model is actually built from rollouts on a real robot. So what we have these low cost robots, and what we did was we basically manually we executed trajectories on this robot and measured how much was the robot deviating from where it wanted to go and where it ended up going. And this led to the development of a noise model that, for this particular robot, this is what the noise characteristics look like. And these noise characteristics, in our case, because we're not doing any training from interaction, these noise characteristics are only used at test time. They're not used at training time to train our method, because our method is not training in an end-to-end fashion, right? It's training in individual modules, and yeah, that's kind of how we are. So it's only at test time, and yeah, it's a distribution. I think it's a truncated Gaussian distribution from which we sample noise, but it compounds over time and the like.
Okay, thanks. So we have a second question. So this is really about the domain gap and generalization, okay, which applies to many robotic settings as well. So the question is this, right? Are there any examples of navigation in novel things, in a novel scenario, what information semantic geometry can better help alleviate the domain gap?
Yeah, that's a good question. I think I would like it to bridge domain gaps in the sense like, let's say I've trained a network in, our hope is that if semantics can transfer, then policies can transfer as well. Now, the unfortunate part is with deep neural networks, we are using the same machinery for, in some sense, inferring the semantics. And if they suffer from domain gap, then we are kind of stuck, right? So in some sense, semantics should help bridge domain gap. If I can recognize a chair in, one kind of images and like a hallway in one kind of images and a hallway in another kind of images, then I could bridge domain gap using semantics. But it turns out inferring these semantics itself will suffer from domain gap in the way we are training them, because they are trained from these deep neural networks. So I think domain gap is a hard, independent other question, which applies to a lot of work in computer vision, much like my own work here, and that requires some treatment. I think in our work, we used these simulation environments, which were derived from real world environments. And so the domain gap is not, we have been able to run policies that were trained in simulation in these realistic environments onto real robots. But I don't know how much is the difference, because I don't know what would have happened if I just trained entirely on real data. Right? So that's a question which is hard to analyze in some sense as well.
Okay, thank you. I think so. The message says that semantics is the abstraction that can address the domain gap, right? Yes, we are looking for different abstractions. Okay, so let's open the questions of panelists. I think we have two experts here. In fact, both Katerina and Hao have given seminar talks in the 3DGV seminar series. So maybe we open the question first to Katerina.
Yes, thank you, Saurabh, for the great talk, very comprehensive. I mean, I know the work a lot and I like it a lot. Here is my question, which is actually related to the previous question. What do you think is going to help navigation to boost the numbers on the benchmarks that are still kind of low, I would say, right? Do you agree?
Yeah, that's a very good question. What are current limitations as to why these models don't work very well, right? Yeah.
Right. And related to your answer in the previous question, you're saying we borrow the semantics of those deep nets. From what I understand is those CNN features are supposed to pre-trained on large-scale data sets, right? But now we have an agent that moves. I mean, we have an agent that can go very close to a chair. It's much easier to recognize a chair if you're nearby than if you are far away, right? So what? I mean, how can we change perception so that we can see better while navigating? Let's say.
Right. I think you bring up a very good question. So I think one of the reasons which we found in our work why the performance numbers are low is so if you have this task of finding chairs, right? In there, I think we have it's a modularized system. So we at the end we have a module which basically tries to detect a chair. If a chair detector from Microsoft Coco trained on Coco fires that, oh, this is a chair, then basically that's when you stop, right? And I think that function itself causes a lot of the if you use an oracle over there, performance is much better. If you use a model that has been trained on the internet data, you just run that model, that works performance is much worse with that. So I think so that aspect is there. I think perception, the way we have trained our models all on internet data, I think there is some gap between internet data and egocentric data. And what you are saying happens, right? Like you can recognize a chair in Coco images in some sense better than you can recognize chairs in these simulation environments. Now it's somewhat unfortunate that these simulation environments are not perfect. I mean, there are artifacts in reconstruction of these chairs and so forth, but there's still a domain gap between models that have been trained on internet data and models that you're trying to run on egocentric data. And I think we need to, so that's kind of certainly one avenue for improving these models, which is we improve these models, like the perception models that we have. I think that will cause improvements. I think the other avenue for improving performance on these tasks, I think, is also related to how much training data can we get for training these representations, right? So if we are stuck with our simulation environments where we have, let's say, 100 environments that we have, and we're trying to learn these semantic priors, what rooms are next to one another, right? You, in some sense, have 100 examples, right? You have 100 layouts, and from there, you're trying to learn about what layouts look like. And I think that is not enough, right? I mean, in some sense, so I think I'm kind of excited about using other sort of knowledge, world knowledge of other forms in order to guide this, that, okay, these objects co-occur. I mean, we tried to do this from videos, but maybe there are other ways of doing this as well. And I think that would be another place where I would look in order to try to improve performance there.
Great, I got you. So what you're saying is let's capture situation knowledge using some other form of knowledge base and coming from somewhere else. And number two, what you said is like using red detectors from Coco on this egocentric data would not work. And this egocentric data, the way I understand it, that you're saying is too little to just train detectors or even fine tune them and somehow get something better, or maybe.
Yeah, I think it is very plausible that you download a detector from Coco and now you can improve it by just having lots of egocentric data, right? And I guess you have some work on that topic, and I think that is certainly something that will improve performance for the models that I was showing over here. I think that's a very good point. Yeah.
Great. One more question is, these topological representations look fantastic and they don't suffer from egomotion mistakes. Do you think they're mature enough and they're going to replace the geometric ones? Or you think there are benefits on the geometric that makes it more robust than the geometric, metric? Yes.
That's a very good question. I would like for, I think topological representations seem or feel much nicer. But I think, but I agree, there are benefits to metric representation. If you can build a metric representation, then, and you can localize your robot inside those metric representations, I think that's pretty good, right? Now, the question ends up being, yeah, if I can build a metric representation, I would, but can I build a metric representation? That ends up being the question, right? And I think if we start running these, so I think all the experiments that we showed, I mean, there was pose error and so forth, but the environment was not changing, right? So I think when we think about metric representations, another aspect to consider is what happens in deformable environments, right? Where, let's say, you go back to your office after COVID, and now someone moves the chairs around, right? Now we want our, I mean, so that's kind of another challenge for metric representations in some sense, right? How do you localize, or how do you do mapping under deformations in the scene, right? Or you have people moving around and so forth. So I think there are enough places where I feel metric representations will be more challenging to develop or more challenging to maintain and so forth. And I think over there, topological representations could help, right? Yeah. I wish I knew the answer to that question. I would like topological representations to shine out and work very well, but time will tell. I don't know yet.
Thank you, Saurabh.
Thank you, Katrina. Thanks for this amazing question.
Thanks, Karina, for the nice question. Then let's move to Hao. Hao has recently moved to robotics and 3D. Okay, at the intersection of robotics 3D, and we would like to have.
Maybe I ask some question a bit closely related to 3D. We're talking about a robot navigating in an environment, and the robot usually should have its physical body, right? It could be big or small, could it be tall or short, could it be wheel-based or like walking-based. Do you consider the body of the robot, like including the collision, or maybe even when it's navigating, it might needs to like look up and down and checking for like possible objects to collide with it. Or like look down to check the local surrounding. This kind of questions.
Yeah, that's a very good point. I think so. In our work, we are not doing that. In our work, we are assuming it's a cylindrical robot of a constant dimension, right? So in the first part of my talk, when I was saying that we are computing optimal actions and so forth, they were computed for a particular robot in mind, and that's how we were training our policies. In subsequent works, what we have done is we have adopted modularization, right? Where we are decoupling this high-level semantic policy from low-level control, right? Mm-hmm. And I think over there, it makes it more amenable for adapting between different between robots with different control spaces or different morphologies, if you will, right? Mm-hmm. That all you need to do is you need to change the low-level controller, right? I guess you don't just need to do that. Where can you go? Like this geometric prediction as to where is free space and so forth. Those will also depend on the size of the robot. But if you assume, it's a similar sized robots, which can differ in morphology, which can differ in how you control them, that would still fit into what I presented here.
Then there's actually kind of a question. I don't know whether it's really a question that you will care about. Like for the question of a collision, right? The question of collision, yeah. Somehow this kind of problem with that needs certain very 3D representation. Maybe, yeah.
Yeah, no, I think, yeah. I could guess where you are going with this. Yes, so I agree. So I think here we are spatializing representations for, you can say, a class of agents, right? Now, if my agent is like a very small, like let's say I'm thinking of like a robot which is like a fetch kind of a robot, right? That's kind of what we are having in mind when we're doing this kind of research. Now, if you suddenly make the robot very, very small, right? You have this right, like now suddenly the world of this robot is very different from the world of the robot that we have in mind, right? And I think you are trying to argue, maybe the point you're trying to make is that if you had 3D representations, if you had explicit metric 3D, then that representation generalizes for both robots.
I'm not asking that question. I'm asking like there are certain modules which I'm not sure whether it's part of like the high-level planning or low-level control. and whether it should be processed by a neural network or should be dealt with certain kind of a geometry analysis algorithm. Yeah, how do we what is the overall architecture and where do we place those modules?
Yeah, I think that's a good point. I mean, yeah, in some sense, I think if we try to optimize for, yeah, yeah, what I'm trying to say is that semantics might be like whatever semantics we're talking about could be different for a big robot and for a small robot. Mm-hmm. Right. If you have a very small robot, I mean, which can go into tiny spaces, I think, I mean, free space semantics or whatever, I mean, will be very different for that versus a big robot, right? So in that sense, yes, there is coupling over here, but I think the coupling is fairly coarse. It's low frequency in the sense it doesn't change too much with the, I mean, maybe there are like 3 buckets we can put things in or 4 buckets we can put things in and things can work out. But yeah, it's a very good question. I've not thought about that.
In fact, I think this question applies. The house question applies to everywhere. Like, so what is really the best trade-off between some of the traditional methods, right? So and the deep learning method. I think this is actually something to, in my mind, sometimes makes the research really interesting, right? Because we don't really have a clear answer yet, and we have to do a lot of research on that. Okay, so I prepared 2 questions, a very general one, right? So what I really see here is that both Saurabh and how you start with 3D vision, right? So the work out, right? Of course, using machine learning now many people, like what I have observed, okay, is that many of the 3D vision, like the jump people, they move into the robotics, right? So this kind of visual navigation. Some of the tasks related to robotics. So I would want to know, for example, so first of all, why this is the case, okay? Number 2 is that what are really like for example, what 3D brings, right? Of course, Saurabh mentioned in the talk, right? So what does 3D brings, like the new, like this kind of fresh air, to this kind of the robotics community, right? The 3D understanding representation system. So maybe we start with maybe how, then yeah. Do you have any thoughts on this? So what motivates you, right? So to work on relevant, right? So to the robotics.
To me, one of the question is, I mean, one of the motivation was the question I was asking. It's like between high-level semantic understanding and low-level like control and this kind of interactions. How do we bridge them?
Okay.
Yeah, what is the representation that we use to bridge them? I guess like I would understand like for vision, for the classical vision, it's question of lifting from low-level sensory signals to like the symbols. But where do these symbols come from? And why is this set of symbols but not the other set? When there should be something that's driving me to think about like we need this set of symbols to fulfill certain high-level goals. But how do we connect the low-level signals to the high-level like functionality-related questions?
Okay. Okay, maybe Katerina, do you have any want to share any insights on this? Right, certainly I see that right. So originally worked on.
I mean, Saurabh has I think Saurabh's architecture that look at the map and there is this perception high-level policy, right? That does perception and chooses a goal to go. And then there's a low-level controller that kind of abstracts from perception, just make sure you go there. I think this is a nice decomposition. Saurabh, do you think this makes sense? This hierarchy and the high-level policy is essentially doing the perception work, and the low-level policy just carries out the spatial reasoning, how to get from one goal to the other, let's say.
Yeah, I think I like the decomposition. I mean, I think it certainly makes training these and so forth also much easier. I think the modularized architecture, because otherwise you're training everything from this supervision of what is the final task supervision, which gets very hard.
Yeah, so I like that. I would expect that navigation should connect more to active perception. Like, I mean, we're stuck with those detectors, but now we can move. I mean, if now we're again stuck, then when we're going to get unstuck, kind of, right? I don't know. I'm pretty sure this is going to be resolved, but I'm just saying that right now people still use the same detectors that we use when we're, from internet images and we're stuck, let's say.
Yeah. Okay, so I have the final question is that for this visual navigation, right? So do you think like advances in 3D vision, like 3D understanding, right? So what would be what would be the potential impact, for example, if we make fundamental progress, right, on this kind of 3D representation, 3D understanding? Do you think this kind of like this field would have the progress on this would have a big impact on this visual navigation, or we should actually just think about the synergy, right, between 3D vision and visual navigation, right? So to create this as a solid field, right, make progresses, or do you think there's still fundamental problems in 3D vision we need to solve, right? So to push this forward. Certainly, representation is, as I mentioned, the Saurabh talk, right? So at the very beginning, you mentioned that those are very important questions.
Yeah. I think we should. I think maybe the message I wanted to give was that we should not just think of 3D as the end goal. I think we should start thinking about why are we doing 3D and what are we going to use 3D for. And I think we need to do both. We need to pursue and push for representations and so forth, which are just good general 3D representations, right? If I find the one right 3D representation that everyone should use, that solves everyone's life, right? That simplifies quite a lot of things. But at the same time, if we just pursue that goal, then we might end up optimizing the wrong thing, right? So for example, I think what I was trying to argue is that representations that do a full 3D reconstruction might be an overkill, and we may not do that. We may not benefit very much from that, and there are certain aspects that are missing in there. So I think we kind of need to do both. We need to, pursue just the pure, what is the right representation question. But I think we should also be aware, okay, here are tasks that I might want to use 3D for. Here is why I am doing 3D, and what do those tasks want, and how could we incorporate those things into our representations? So I think there is there's scope for doing both things, I would say, in the field right now. And I think that's certainly why I moved from doing purely 3D, answering the question, what can I do for 3D? That's what I was doing earlier, right? And now I think what I'm trying to ask the question is, what can 3D do for me, right? And I think we need to ask both questions. I think just one is not enough.
Yeah. So the message is putting 3D in the big context, right? So really this kind of end goal, right? In those tasks. Yeah. Okay. So then maybe since time it's already like 22+2 here local time. So let's thank Saurabh again for the wonderful talk, and thanks all the panelists for sharing the insights. And I think this is the visual navigation, right? So this is a very promising field, and it connects to many things. And I hope we'll have great work coming out from all of you and from this community in the near future. Okay. Thank you for the attention. Okay, thank you.
Yeah, thanks a lot, everyone.
Yeah.
Thanks for.
Thank you, Saurabh. Thank you.
Okay.
Thanks for organizing.